to, we've got all the equations, okay? Now we just have to know, make sure we know how to use them, okay? So I'm going to walk through some sample problems, do some demos about how gravity is explained and how that works, and then I'll turn you loose. So that's kind of the plan for the day. So let's say, hypothetically, that I gave you this problem. So satellite has an orbit that is 122 kilometers above the surface of the Earth, which is about 50 miles, which is kind of the distance like from here to, I don't know if you never, like if you know where like Cassidy is, okay, that's about how high it is. So you only have one number, the 122 kilometers, but I want to find the velocity, the orbital period, the centripetal acceleration, and the value of the gravitational acceleration at that point. So Miss Pfeiffer, what's the first thing that you're going to have to do with this problem?
Find the velocity.
No. Before you can even start to do that, what are you going to have to do? What units is this in?
Oh, change it to meters.
Okay. So how are we going to do that? Are we going to multiply by 1,000 or divide by 1,000?
You're going to divide by 1,000.
So if I divide by 1,000, I'm going to get 0.122 meters, which is about like that.
Oh, you're going to multiply.
Let's multiply. Okay? All right. So this is this distance. Let's change it up. Let's see that a little bit. So that's that distance to the surface. Okay? So we get 122,000 meters. So is this what we're going to use as our radius?
No.
No, it's bad. Okay? What are you going to have to do to that value? Where does that distance have to be measured from?
This
Center of the Earth, right? So it's 122,000 kilometers above the Earth. So what are we going to have to do?
Turn them both into points.
That's true. That is true. We're going to turn them into point masses. So I need to know the distance from this point mass to that point mass. But I only have part of the distance, so how am I going to get the total distance? What am I going to add to that number? Let me give you a hint. It rhymes with radius of the Earth.
Radius of the Earth.
Beautiful, okay? Because it has to be, you're right, it has to be a center-to-center distance, because we're going to treat these things as point masses. So we're going to add the radius of the Earth. Now, when you add the radius of the Earth, don't round this number, okay? Keep this number. Do not round it. So Matt, do us a favor. Take 122,000 and add that to the radius of the Earth.
You got 6493300.
So 6.49
33 E6.
times 10 to the 6th meters. Now I can find the velocity of the Earth, okay? Because I promise you, this is what you're going to do wrong. You're going to see 122 kilometers and you go, oh, there's my radius, okay? And you're going to put that number in and you're going to get an answer that makes absolutely no sense whatsoever. So, now here's what you have to be careful of as far as the wordage on problems. When you get a radius, it's going to be either one of two things. It's either going to be the distance above, or it's going to say, oh, here's the orbital radius. The only time you have to add in the radius of the Earth or the radius of the Moon or whatever it is if you're specifically told this is the distance above it. If you're told this is the orbital radius, then that's already measured from the center of that object out to where you are. So you only add in the radius if you are told that's the distance above it. Okay? So just be careful about that. All right. Now, once we have this, we can go, oh, okay, hey, velocity equals big G, mass of the Earth over R. So then it's just a plug and chug affair. So we got 6.67 times 10 to the minus 11th newtons meter squared over kilogram squared times the mass of the earth, 5.979 times 10 to the 24th kilograms, divided by 6.4933 times 10 to the 6th meters. Now, if you all remember from yesterday, okay, we're in a near-Earth orbit. What should be the magnitude of my velocity? 10 to the third. What's going to be the orbital period in seconds? To the third. If you do not get those numbers, you have done something horribly wrong. Okay? I promise you, there's going to be no tricks. It's like, oh, Brooke has to be the jerk. He's going to make it where we get like 10 to the 5th. Okay? No, I can't. I'm not. Honest God, if you do these calculations, whether it's the moon, the earth, you're going to get 10 to the 3rd. If you don't, you have done something wrong. Okay? I'm not going to trick you on the test on Friday. You're going to do calculations like this. If you don't get 10 to the 3rd, stop. Okay? You have done something wrong. All right, so Matt, what do you get when you actually crunch the numbers?
7,836.
7,000 what?
836.9.
So 7,840 meters per second. So 7.84 times 10 to the 3rd meters per second. Okay? And this is what we talked about yesterday. Okay? That's about 5 miles per second. So that's like going from 53rd and Mays Road down to 13th and Mays Road in 1 second. Okay? This is why it's so hard to get things into orbit, because of the fact that you have to throw them so fast. Okay? They have to be moving at such a high velocity. But the cool thing is that once you get them moving, okay, then you don't have to keep firing the engines, because they're just going to be in this continuous state of free fall. And again, here's the main idea. As this satellite is going around the moon, or around the earth, or whatever it's going around, what's creating the centripetal force to keep that thing in motion?
Gravity.
Gravity is. Okay? And the direction of that force is where, Kara?
Downward,
We're going to get towards the center of the earth and at
90 degrees.
to the,
Oh, the
rhymes with velocity vector.
velocity vector.
There you go. Velocity vector. Okay? Right? There you go. All right, so we got that one done. Pretty cool. Now, remember this number, 7840. We're going to need that number later on. So now we need to find the orbital period of the satellite. Now, what you all have, I'm going to move down here. So what you guys have on your equation sheets is this. Big G mt squared equals 4 pi squared r cubed. Okay? This is what you guys have. You've got to be able to solve this equation either for T, R, or mass. Now, Shivani, is this the mass of the satellite, or is this the mass of what it's orbiting?
What it's orbiting.
Beautiful. This is never, ever, ever the mass of the satellite. Why is it that the mass of the satellite?
Because the satellite doesn't matter.
Yeah, the mass of the satellite doesn't matter. It doesn't change anything. Okay? The satellite could be a garden pea. The satellite could be the International Space Station. Doesn't matter. The only thing that determines this is going to be the mass of whatever is at the center of that orbit. The moon, the earth, whatever that is. Okay? All right. So, we need to solve this for t. So, Shivani, how am I going to get t by itself? What am I going to do?
Divide GM and then square root it.
Beautiful. So period is going to equal the square root of big G, mass of the earth. Excuse me, I screwed that up. I put it in the wrong place. 4 pi squared r cubed over big G, mass of the earth. So we got 4 pi squared. What was that radius?
6.4933 times 10 to the 6.
I love this little bit right here. And look at that. Oh. hold on. That didn't work so well. I'm just gonna write it again. What was it? I tried to get clever with it. What was it?
4933 times 10 to the 6.
Beautiful. Now that's gonna get cubed, okay? Don't forget to cube that. And then you got big G, mass of the earth, okay? And again, this should work out to be 10 to the third. So, Matt, or somebody run the numbers. Here's the most common mistake that you will make, is that you'll forget to cube that radius. That's the most common mistake that's made.
5206.
What'd you get?
5206.
5,206 seconds. Can you divide that by 60, Matt?
86.7.
86.7 minutes. So about an hour and a half. Okay? All right? Okay. That's just kind of a plug and chug type affair. We got that one. Okay? All right. So the next thing we need to do, we got two of these things done. We got the period. Now we need to calculate the centripetal acceleration. Now there's two ways you can do your centripetal acceleration. I don't care what you do. You can either use v squared over r, or you can use 4 pi squared r over t squared. Okay? I don't care. Pick one. Matt, which one do you want to do?
V squared over r.
Okay, so we're going to use v squared over r. We said the velocity was 7,840 meters per second. And again, we're going to use the exact same radius that we've been using, okay? Because it's measured from the center of the earth. And that radius was, now Matt, step away from the calculator for just a second. 6.4933. Okay, now let's just get an idea of our order of magnitude. Okay, so Kara, this is 10 to the third, right? But I'm going to square it, which is going to give me 10 to the
6.
10 to the 6. So I'm going to take 10 to the 6 and divide it by 10 to the 6, which gives me 10 to the, nope,
Wait, well, what did you just say?
10 to the 6th
Okay.
divided by 10 to the 6th.
So-
10 to the,
0.
and anything raised. So here's the point.
1.
This isn't going to be a very big number. Okay? If I do this and I get a big number, I've done something wrong. Okay? That's what I want you to see. Okay? This should not be a very big number. So, now Matt, what did you get?
9.458.
What'd you get? 9 point?
9.459.
So 9.46? Rounded?
No, because we'll only have 4 significant digits in the kilometers.
Well, but I got the 7840 with 3 significant digits.
Right, but shouldn't have that been 4?
So 9 point what?
4, 5, 8, 9. 7, 4, 6.
Okay, we're good?
Sure.
9.46 meters per second squared. Okay? We're good. All right. Now, notice that that is less than 9.8 meters per second squared. Just going to plant that seed. We're going to revisit that. But notice that that is less than 9.8 meters per second squared. Now, at this point, the only thing we have left to do is calculate little g. Okay? Now, little g is not a constant. So, little g equals big G, mass of the earth, over r squared. Okay? Little g is not a constant. If it was a constant, we'd call it big G, which is 6.67 times 10 to the minus 11. So little g changes, okay? It depends upon where you are relative to the earth, okay? It is not a constant. So this is going to be big G, mass of the earth, and we have that radius of 6.4933 squared. So, Matt, run those numbers again, if you would, please. And by the way, in case you haven't noticed, on about everything, it's big G times the mass of the earth. So, that's why I said if you were doing these computations by hand, you would do this calculation and then you would have that as like a separate number so you didn't have to recalculate that value every time. So, let me know what you get, if you would, please, Matthew.
Same thing.
Oh, get the same thing. Oh, crikey, as they say in Australia. Oh, I get 9.46 meters per second squared. Coincidence?
Yes.
I think not.
It must be. I mean, how else would you
Well,
get the
yeah.
same number?
I know, just random. No, so
Science is
here's
full of coincidences.
Here's the deal, okay? This is one of the most important things that you have to get. So here's the Earth, right? Okay? So on a scale, if this was the size of the Earth, this satellite would be about a half an inch above the Earth. Okay, that's all the farther it would be, about a half an inch above the Earth on this scale. Okay? So when you're there, okay, and there's a couple of ways you can view this number. Imagine that you're standing and visualize this. Here's the Earth, and we're going to build this really, really, really tall ladder, okay? And Shivani is going to be standing on top of this really, really, really tall ladder. That's 120 kilometers tall, okay? Shivani's going to stand up there. It's like, you can handle this. Shivani's up there. She says, oh, I'm a little nervous, Burkamp. You're going to do fine, okay? And she's going to take a golf ball. There it is. A golf ball, right? And let's start with this idea. She has a golf ball that has a mass of 1 kilogram. It's a big golf ball, okay? She has this golf ball has a mass of 1 kilogram. She's standing on top of that ladder. At this point, little g is 9.46 meters per second squared. She takes that golf ball and she hooks it up to a Newton scale, okay? What should the reading on the Newton scale be when she's on top of that ladder?
9.46.
9.46 newtons. Why?
It's just 1 kilogram.
Because Fg equals mg, right? So at that altitude, she's standing on top of this really tall ladder. If she takes that Newton scale and she hooks it up, it's going to read 9.46 meters per second squared. Now she goes, wow, this sucks. I hate heights. I'm going to climb down.
How did you know?
I don't know, just a guess, okay? So she's going to climb down. She goes, okay, I'm done with science experiments. This is stupid. She climbs back down to the Earth. Now she's standing at the surface of the Earth. She takes that same 1 kilogram mass and she hooks it up to the Newton scale. Now what's it going to read?
9.8.
Now it's going to read 9.8 newtons, because at the surface of the Earth, g is 9.8 meters per second squared. So the farther and farther and farther you go from the surface of the Earth, g becomes smaller and smaller and smaller. So if you were to look at a graph of g versus radius, okay? And you were to start here at the radius of the Earth, that would read 9.8 meters per second squared. So as you go further and further and further from the surface of the Earth, guess what? G is going to become smaller and smaller and smaller. So at that altitude, if she's standing on top of this ladder, that scale is going to read 9.46 newtons. She comes back down and stands on the surface of the Earth, vowing never to do a science experiment again. Then it's going to read 9.8 newtons, okay? So little g changes, okay? And it changes inversely with the square of the distance. Now, here's the other way that you can view this story. Shivani is standing on top of the ladder, and she lets go of the golf ball. She lets go of the golf ball. The acceleration of that golf ball isn't going to be 9.8 meters per second squared. It's going to be 9.46 meters per second squared, okay? Because I'm farther from the center of the Earth. So there's a couple of different ways you could view this. Now, then Shivani goes, okay, I'm gonna show Burkamp. I'm gonna take the golf ball and I'm gonna throw it, okay? And I'm gonna throw it so fast that it's gonna be in orbit. Oh, that's gonna be cool, right? She's gonna right? Throws it really, really fast. So the golf ball is gonna take off, but the golf ball is going to begin to fall because it's in a gravitational field. And it's going to undergo centripetal acceleration because it's traveling in a circular path and it isn't traveling straight like it wants to. So here's the main idea. That centripetal force is created by the gravitational force. That's the recurring theme of this story, okay? Well, your centripetal force is mass times your centripetal acceleration. Your Fg is mass times g. Well, little mass cancels out. Your centripetal acceleration equals your gravitational acceleration. So no matter where you are, okay, with the Earth, as long as you're in orbit, whether you're a near Earth orbit or you're a GPS satellite way out here, if you're the moon, doesn't make any difference. Wherever you are in orbit, your centripetal acceleration is the exact same as your gravitational acceleration, because your centripetal force is creating your gravitational force. Okay, so that's one of the most important ideas that you have to have. And the other thing is that that value of little g is not dependent upon the mass of what you're holding. The only thing that determines little g is two things: the mass that you're falling towards and how far you are from it. So this is why when you drop something, a golf ball, a bowling ball, Kara, doesn't make any difference. Everything's going to accelerate at the same rate because they all have the same value of little g, because the mass of what's falling does not matter. Okay? Got that? Good? Fantastic. Okay. So we got that problem done. Now, I promise you, you're going to have a problem like this on the test and on your assignment. So let's make sure everybody's cool with this. So we look through a telescope and we find a new planet, and we are also observed that it has a moon. Okay? And we watch the moon. And the moon, we know, takes 20.5 hours to complete one loop around the planet. Now, how long does it take our moon to complete one orbit around the Earth? Roughly.
28 days.
Yeah, about a month, okay? About 28 days, okay? Because the fact that you get a full moon about once a month, okay? You get a full moon, okay? So that's about how long it takes. This moon only takes 20.5 hours. That means it's, relatively speaking, it's much closer to the surface of this planet than our moon is to the Earth, okay? Because it takes a long, it doesn't take very long to orbit. So it also has a radius of 3.68. Now, notice on this one, I did not tell you that's how far above the planet. When I tell you this, that is already the distance from the moon to the center of the planet. You don't have to add in the radius of the planet. Number one, you don't even know what the radius of the planet is. Couldn't do that even if you tried, because you don't know that number. But here's the point. Pay attention to the verbiage. That's that radius. You already have that dimension. Okay. So, you're going to start with GM t squared equals 4 pi squared r cubed. So what do you want to solve for? What are you going to solve for?
The mass.
Mass. So Shivani, what's that going to look like solved for mass?
Divide by gt squared.
Beautiful. Now, what are you going to do wrong with those 20.5 hours?
Put it in hours.
But what are you going to do wrong with it? What are you not going to do?
Just divide by 60. Oh, wait, square. Right? No?
Okay, here's the point. What units does this t have to be in?
Seconds.
Seconds.
That's
Okay?
what I said.
Oh, I didn't, okay, I
You
misunderstood
said it
what
wrong,
you
I said put
said.
in hours.
So you're going to take 4 pi squared, okay, r cubed, it's a pirate thing, okay, and then you're going to divide that by big G, and then you're going to take 20.5 hours, and you're going to change that into, and 1 hour is, how many seconds? 3,600 seconds. There's 60 minutes in an hour, right? So that's going to be 3,600 seconds. And then then you're going to forget to square that as well. Okay? So you're going to do two things
Sorry. It was just something right there.
Okay? So you gotta change this into seconds, and then you gotta square it. So what do you get out of all that, Matt?
That's not correct.
Don't forget to square a pi. So you can have 4 pi squared times that number cubed divided by g. And some people, like, they'll get this number first, they'll square it, then they'll multiply it by g. If you want to type it in all at once, you can. I always like to divide and conquer. So what do you get? What?
I got 5.42 E21.
Yeah, that's what you get.
Oh, okay. Okay, good, we're good.
Yeah,
Was the max, so what did we
we're good. Okay? So this is actually how we find the mass of planets, is that we observe things that orbit it, and then we work backwards and we find the mass of that. That's how we find the mass of Jupiter, Saturn, all that stuff. Yes, Shivani?
Oh, no, I have a headache.
Oh, I thought you had a question.
No.
Okay. All right, so let's take a stretch, and then we've got one more problem to work, and then we'll be done. So, we're having a what?
A spiky party.
Oh, I thought you said spicy party.
My
That
favorite
too,
thing.
that too.
Okay. So,
If your parties aren't spicy, then are they really parties?
and if you get done with the test tomorrow, or on Friday,
Oh, God.
on Friday, on Friday, or if you get done with the assignment, and you haven't done a problem like this to find the mass of a planet, you have done something wrong, okay? Now, I promise you what you're gonna do wrong is I'm gonna give you that orbital period in hours or days or something like that, and you're not gonna convert it, and you're gonna get an answer that makes absolutely no sense, okay? So, I'm just telling you, that's what you're gonna do wrong. And you sit there and go, Mr. Burkamp, we won't do that, and you lie. Okay. All right, so, here's the story on this one. So the moon has a radius of 1.40 times 10 to the 5th, and again, that is the radius. You don't have to do anything with it. That is the radius. And so let's say you've landed on the moon, Shivani has landed on the moon, and she drops a rock, sets up a pendulum, whatever. And she figures out that little g has a value of 1.22 meters per second squared. So I want to find the mass of the moon, and then what would be the distance from the center of the moon so that a 1 kilogram mass weighs 1 newton. So let's talk about this first. So you know what little g is, right? So Kara, what relates little g, the mass of the planet, and radius?
What, the equation?
Yep,
Little g?
yep.
Give me a second. It's not, oh, I was gonna say g, like capital G,
It is
mt squared.
m over r squared,
Oh, yeah, that works.
right?
Yeah.
Okay,
Oh my, yeah, sorry.
Good.
This is a little slow.
okay, we're there. Karen, we're there. That's all that matters. Okay, we're there. So, Miss Pfeiffer, I need this solved for mass. So what am I going to do?
Multiply by r squared and divide by
Big G, right? So I've got 1.22 meters per second squared times that radius, which is 1.40 times 10 to the 5th meters squared, divided by 6.67 times 10 to the minus 11. So, Matt, can you run these numbers for me? Or did you already?
Nah, I'm not.
You slacker. Come on, you're usually like, oh,
Okay, every time I do it, you tell me not to crunch the numbers yet, and then
Okay.
every time I do, I try and balance it.
Well, this is 10 to the 5th so squared, so that's 10 to the 10th, divided by 10 to the negative 11, or about 10 to the 21st. Ballpark. So let's get
1.4. Oh, okay. Sorry. Just a little slow today. 2.56 E15.
What'd you get?
2.56 E15.
Oh,
Oh, I didn't square that. My bad.
yeah.
You want to do this, Karen?
No.
You kind of set yourself up on
I know.
the first day. Yeah, I don't even have to.
What was the number we agreed upon?
It's like something around 10 to the 21st.
Oh, okay, so it is 3.58 or 3.59 E20.
That's 10 to the 20th kilograms. Okay? All right? Now, here's the magic code. What would be the distance from the center of the moon so that a 1 kilogram mass weighs 1 newton? So here's the magic code, right? So if you look at Fg equaling mg, so if I have a 1 kilogram mass and I hook it up to a scale, and the scale reads exactly 1 newton, what does little g equal at that point? 1 meter per second squared, right? Because if I take 1 kilogram times 1 meter per second squared, I get 1 newton. Everybody cool with that? Okay? So, what I want to do is I want to say, I want to know where I have to be so that basically little g becomes 1 meter per second squared. Now, clearly, my answer has to be bigger than 1.40 times 10 to the 5th, because at 1.40 times 10 to the 5th, okay, that's where little g equals 1.22 meters per second squared. So I've got to be at some distance out here away from the surface of the moon so that little g becomes 1 meter per second squared. So I know my answer has to be bigger than this, okay? So just go back to that equation that Kara said, okay? So we'll go back down here where we have little g equals big G mass over r squared. Now at this point we know the mass of the planet, right? We know that. This mass is not the 1 kilogram, okay? It is not the 1 kilogram. This is the mass of the planet because it's the mass that it's falling towards, not the mass that it's following. So, Kara, I need to solve this for radius, so what am I going to do?
Multiply by radius squared and then square root it.
So I've got gr squared
I'm
equals
sorry.
big GM, then what?
Divide by g and then square root.
Beautiful. Okay? So I'm going to take big G, and what do we get for the mass of the planet? Where's the mass of the planet?
3.59 E20.
3.59 times 10 to the 20th kilograms divided by 1 meter per second squared. And what do you get, Matt? Ho, 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 ho.
Yeah, that's what I said. Okay, we got 1.55 E5, and then subtract the.
No.
No? You don't want to know how
Hold
far
on.
the surface it is? Or did I read it?
No, I said what would be the
Okay, cool.
distance from the center of the moon?
So just, yeah, 1.55 E5.
Times 10 to the 5th meters. Now, if I did ask, you do have a valid point. If I had said, how far above the surface of the moon would you have to be for that to happen, then you would subtract out the radius. And you are going to have some problems like that on your assignment, where I say, like, how far above the surface of the Earth is this going to happen? Okay? So if I ask, you find a radius, and then I ask how far above the surface, then you subtract out that value, okay? But if I just said, what's the center to center distance? Just leave it as is. Okay. All right, so let's talk about what gravity is and what gravity isn't. So if you look at, in the sequence, Kepler comes up with his laws. Law of ellipses, law of equal areas means it moves faster when it's closer, slowest when it's further away. And then he has his third law, which is, TA squared over TB squared equals RA cubed over RB cubed. Okay? Kepler makes no mention of gravity, anything like that. Newton comes along and he says, look, here's the calculations, but we really didn't know how it worked, okay? We could do the calculations, but as far as the visual, as far as how gravity works, that was a little sketchy. So, let's go to the back of the room, and we're going to see how Einstein viewed space and time and gravity.
I can never read them.
Okay, so let me get you started on problem number 10, okay? So, problem number 10 looks hardly difficult. A lot of that is just explaining the situation. So, I'm going to get you started. So, here's the Earth. Here's the Moon. And here's the Lunar Excursion Module, okay, that we fired from the Earth and we're going towards the Moon. So, I want to find the first point, L1, is going to be the position where the gravitational pull back towards the Earth is exactly equal to the gravitational pull towards the Moon. So if you were to look at like a cross section in terms of like a gravitational well, I'm trying to find the crest of the two gravitational wells, where I would put it and it would just stay exactly balanced. If I go past L1, I'm going to go down the gravitational well of the Moon. If I'm not going fast enough, like Matt said, it's like riding a bike, and I would coast up the hill, and then I would start back down. So I'm trying to find the position of the crest of that hill. Now, is the crest of that hill going to be closer to the Moon, closer to the Earth, or right in between?
Closer to the Moon,
Closer to the Moon. Why, Shivani?
because it has a weaker gravitational pull than Earth.
Fantastic. Okay, that's a weaker gravitational pull. So I know whatever this distance is, has to be closer to the Moon. Okay, because it's a more shallow gravitational well. It doesn't have a stronger gravitational field, however you want to think about it. Now, here's one thing I want you to get out of your minds. The Lunar Command Module is always in the gravitational field of the Moon. Okay? Right now, you all are being pulled by the Moon. Okay? Not very much. Okay? It isn't like, wow, there's a full moon. I'm going to be lifted off the Earth. Okay? No, the gravitational pull towards our Earth is a lot stronger. But as this thing goes, the pull from the Earth is going to get weaker. The pull towards the Moon is going to get stronger. And even after you cross this point, you're still in the gravitational pull of the Earth. It isn't like, oh, I crossed this point and we shut off the gravitational pull from the Earth. You're not. Just the net gravitational pull is going to be towards the Moon. Prior to that, the net gravitational pull is towards the Earth, and right in the middle, it's like a tug of war, and you're caught in the middle, but you're like a chew toy between two fox terriers, okay? And you're the chew toy, and you're being pulled in both directions. All right, so I'm going to get you started on this. So basically what we're going to say is that the force between the Lunar Command Module and the Earth is going to equal the force between the Lunar Command Module and the Moon. Okay? That's how we're going to start this problem. So this is going to be big G, mass of the Lunar Command Module, mass of the Earth. Now, in the problem, I tell you that this distance from the Earth to the Moon is 3.844 times 10 to the 8th meters. So you know the entire distance, okay? You know the entire distance. Now, what we're going to do is we're going to let this distance from the Earth to the Lunar Command Module be x, okay? We don't know what it is. We're going to let this distance be x, okay? Now, if this distance is x, and the entire distance is 3.844 times 10 to the 8th meters, what's left over? Don't make this difficult.
3.844 times 10 to the 8th minus x.
Yes, okay? If I take that distance minus x, that's what I have left over. So those are going to be my two distances. So I'm going to let this be x, but that's going to get squared, okay? Now, that has to equal big G, the mass of the lunar command module, times the mass of the moon, divided by 3.844 times 10 to the 8th minus x squared. Okay? Now, let's simplify some things. Miss Pfeiffer, do you think I can cancel out my g's? Yeah, that goes away. Okay, that's going to make life simpler. I don't have to worry about those. What else can I cancel out?
Mass of the lunar.
Beautiful. Guess what? I never gave you the mass of the lunar command module. You know why?
It doesn't.
Doesn't matter. It's going to cancel out. Now, here's what we're going to do at this point. We're going to cross multiply. Okay? So we're going to take the mass of the Earth, we're going to cross multiply, okay? Times 3.844 times 10 to the 8th minus x, quantity squared, is going to equal the mass of the moon times x squared. Okay? Now, this is going to work out to be a quadratic. So I want to simplify this as I can. So I'm going to divide both sides by the mass of the moon. Okay? So you got, and I gave you the mass of the moon. It's up there on problem number 8. It's 7.35 times 10 to the 22nd kilograms. So if you take the mass of the Earth and divide it by the mass of the moon, trust me on this one, you get 81.35. So if you take the mass of the Earth, 5.979 times 10 to the 24th, and divide that by the mass of the moon, you get 81.35. Okay? So what this means is the Earth is 81.35 times more massive than the moon is. Okay? That's what that number means. Now, at this point, I got 3.844 times 10 to the 8th minus x squared equals x squared. Okay? Now, yes, ma'am.
How come you can only divide it, you can only divide it by the mass of the Earth? You don't have to divide the whole side.
Well, because they're multiplied by each other, if you divide one of them by it, it'll have the same effect.
Oh.
Yeah, I could distribute that and then divide everything, but it would just be a god-awful lot more work. It's going to have the same net effect at the end. Okay? Now, at this point, you have a decision to make. Option number 1. This is option number 1. You expand this binomial. Okay? Remember like the FOIL method? So, you're going to write this out, and you're going to expand it. And you're going to take this times itself. You're going to have x squared, and you're going to take this times negative x multiplied by 2. And then you're going to distribute 81.35 over all of that. And then you're going to move an x squared over there, and then you're going to use the quadratic formula. Okay? So if you really want to do a really, really hardcore quadratic formula, expand this, distribute the 81.35, subtract an x squared, so one side equals 0, then plug it into negative b plus or minus b squared minus 4ac all over 2a. Matt?
What if I don't want to do that?
Well, let's talk about that. Okay, I'm just telling you, that's an option. I'm not saying it's a good option. I'm just saying it's an option. Now, could I take the square root of both sides?
No. Because
Sure I
it's
could.
Squared.
I could take the square root of both
Never
sides.
mind, we can take the square root of both sides.
Okay, I could take the square root of both sides. Matt, get me the square root of 81.35.
You got 9.02.
Plus or minus 9.02, right? And this is going to be important. It's plus or minus 9.02. Guys like the square, what's the square root of 4? Plus or minus 2. Now, when I take the square root of this, because that's x squared, that's just 3.844 times 10 to the 8th minus x. equals x. Okay? Now it becomes much simpler to solve. Now, this is where I'm going to leave you on your own, but I'm going to tell you what to do. This is how you're going to get your two possible solutions, because it's a quadratic. The first thing that you do is you're going to take positive 9.02, and you're going to take 9.02 times all of this, times this number, and times negative x, and that's going to get you values over here, and that's going to equal x. Then is one variable, one equation, get all your x terms on one side, get your numbers on the other, divide it out, there's one solution. The other solution is that you're going to start over, you're going to take negative 9.02 times everything, and that's going to equal x. Then you move your x terms to the other side, get numbers on the other, just like you would any algebra problem. So you're going to work this twice. Multiply 9.02 over it, solve it as an algebra problem, take negative 9.02 and do this. So what you're going to see if you do this right, you're going to get two possible Lagrange points. One of them puts you between the Earth and the Moon, puts you right here. The other one puts you outside the orbit of the Moon. Okay? Those are your two possible solutions. One's in here, one's out here. Okay? That's what you got. All right. Now, let me give you some hints on some of these problems and how you want to tackle them. So, if you look on, like, number 2, okay? So, number 2, you're told that two identical spheres, meaning they're going to have the same mass. So, here's my two spheres. And they're separated by 1.20 meters. Okay, so 1.20 meters is about like yay. So imagine I've got two spheres, one here, one here. And they're going to feel an attractive force of 1.00 times 10 to the negative 4th newtons. You want to find the mass of each one. Okay, so you're just going to go, oh, F equals big G, M1, M2 divided by D squared. Now, you don't know the mass of one, nor do you know the mass of two, but they're identical. So what are you going to let the mass of one equal? No. You can't let it be 1.
Half.
No, just a variable. Let this be x. Okay? You don't know it. Let this be x. Since it's identical,
All right.
what's the mass of this going to be?
X.
X. Now, if one mass was twice the other one, if you let that be x, that one would be 2x. But they're identical. So this is just x and x, right? So when you take x times x, what do you get?
X squared.
X squared, not 2x, you get x squared. So you're going to have F equals big G, x squared divided by D squared, solve for x. Okay? Now, when you get to question number 3, at what center to center distance from the Earth would a 1 kilogram mass weigh 3 newtons? Okay? So here you are on the Earth. If I have a 1 kilogram mass on the Earth, that weighs 9.8 newtons, right? Because if I take 1 kilogram times 9.8 meters per second squared, I get 9.8 newtons. So what I want to know is basically how far I have to lift this thing up so that when I hold it up by a scale, instead of reading 9.8 newtons, it's going to read 3 newtons. Okay? Now, if it weighs 3 newtons, what is little g going to be if it weighs 3 newtons? I always said if I became a rapper, that would be my rap name, Little G. Give it up for Little G. Yo, what's up? So, what is little g going to be if a 1 kilogram mass weighs 3 newtons? 3 meters per second squared, right? So you're going to go little g equals big G mass of the Earth over r squared. This is the mass of the Earth. It is not 1 kilogram, okay? This is the mass of the Earth. You know what big G is? This little g is going to be 3, solve for r, okay? Anyway, so let me give you some hints on some of the answers. Let me see. Your answer to number 2 should be something times 10 to the 3rd. Your answer to number 3 should be something times 10 to the 7th. Your answers to 8 and 9 are both something times 10 to the 3rd. Your answer to number 12, when you're finding the mass, I think, of Saturn, that should be 10 to the 26th. Yeah, there's the backside. Now, on number 16, you're going to go old school, that equation. Okay? Old school, you're throwing something up in the air, old school, that equation. On 18 through 20, that's involving escape velocity, and that equation is on your lecture notes, but I'm going to give that to you. So that's 2 big G M over R. Okay, it's also in your lecture notes. You have to write down the definition, so make sure you read that. But that's your equation for escape velocity. I'm done. Good luck. Now, this assignment is actually due on the test day of Friday, but I would suggest that you not wait until Thursday night because you're going to study. You got a bunch of other things to do. Tomorrow, I'm going to work through any specific problems that you want. So I would at least work through all of these problems. If you come across a problem, you go, okay, well, I have no idea how to do this, then we need to talk about that tomorrow. Okay? All right, Matt?